Today we're going to be talking about top K problem or problem of heavy hitters. In a lot of services, we need to extract subset of much bigger set for something. As an example, we want to get top 10 viewed YouTube videos for some period of time, let's say for the last hour. You want to get top 20 liked Instagram posts for this day. Or you want to get top 10 most bought products on some marketplace. Whatever the service is, general stuff will be the same. You'll have something like IP gateway, basically service responsible for routing all the requests from users to downstream web backend services. And this service can also be used to somewhat partially solve this problem for a simple case, at least. All right, let's discuss functional requirements that we have here. That's a pretty easy one, because we only want a function that will return top K list, or something like this. Basically, as a functional, that's it for some specified time, of course. Specified time period. All right, for non-functional requirements, we have quite a list because we want it to be, of course, scalable. We want it to be performant, because generally when you want to see popular something, you want to get result pretty fast. And we want it to be available. It will be not great to see like internally loading page when I want to view top something, top post or top videos. All right, I think we will stay on these three. And so continue the next section. Now let's discuss foundation of system design. We will be talking about single server case. So it's early days of our Instagram, and it got not a lot of posts and not a lot of users. So we can keep everything to one server. So we get our requests, IP gateway process them, and then it generates events of viewership of some posts. So basically we have view of ID1 post, ID1 again, ID4, and so on. We are talking about some specified interval. Let's say for simplicity that we were talking about every minute. We are going to flash this Hashmap into our sorted list or min-heap and keep everything into storage. Like saving, we calculate this and then just flash it to storage and then start again. So this allows us to show top K for every minute. All right. Now let's talk about why we have two options here. Our Hashmap just keeps track of how many times a certain post was viewed. And then we can go two ways. Either we can sort this Hashmap and get ourselves with nice sorted list from which we can just extract top K. Let's say, for example, we can say we want top 2 viewed posts. We can just extract ID4 and ID1 and get ourselves top K. This will require time complexity of big O of n log n because we need to sort this Hashmap with n elements. Also, we can suggest as a solution which will save ourselves a little bit of time or a lot of time, depending on how big is n. Min-heap, which is a binary tree where every node has a value less than or equal to its children. So in min-heap, we only need to keep k nodes because we don't need more. And time complexity of operation will be n log k because log k is the time we need to remove from heap, and n is number of our unique IDs. So basically, maybe we would need to remove every ID, or specifically n minus k, maybe something like this. But okay, generally it will be n log lk. All right, now let's move on to more deep dive into system design. Let's refine our system design. Now we are back to high load and big service. So we need load balancers to route our user requests to IP gateways, which are going to be many now. IP gateway get event of say like on some post. So we have an ID and the event of like. IP gateway then sends this event to messaging queue, which also distribute, of course. And after this, we have preprocessor service that's going to be taking these events from messaging queue and processing them as discussed above into Hashmap and then to min-heap. Let's say we assume k equal 2, then min-heap is going to be taking only 2 elements. Now that every preprocessor server finished with min-heap, we will be talking about collecting data for 1 minute. So every 1 minute, we are going to be flushing this min-heap toward messaging queue and starting a new calculation. All right. Now that we have our min-heaps in messaging queue, merge server is going to be taking them all from queue and merging, of course, as name suggests. Basically, all min-heaps have unique IDs, so there is no intersection between them. So we just need to choose top 2 from all our min-heaps. So basically, it will be ID 6 and ID 4 when we consider these 2 min-heaps merging into one. All right, great. Now let's discuss about storages that we're going to be employing and strategies. All right, now let's recap. We have our min-heap merged. Every minute it's in U1, and we store them in some storage. All right, but how about if we want to calculate top K for 30 minutes or 1 hour or whatever? We cannot do it from 1 minute heaps because on every minute we may have some other IDs shuffling around, and every time ID does not get in this final merged min heap, we miss it from calculation. Which creates misses when we want to calculate overall. So in order to calculate this, we would need to be keeping our events stored at some place like storage, and the most suitable one would be distributed file system, because we would need to store a lot of events. Also, next best thing would be to store these hash maps of chosen granularity. In our case, we was talking about 1 minute, but it can also be like 10 seconds or 20 seconds, something like this. I guess we can say that we're going to be storing these hash maps of 1 minute into storage. This will allow us to save some space and ease up our task. But generally, if you want the best granularity possible, you would need to go from messaging queue to storage, not from preprocessor to storage. All right, so basically, let's just copy another storage, and maybe let's specify that it is distributed file system. All right, so we're going to be keeping these hash maps towards storage, but in order to arrive to our heap, we would need to run another processes from it. So basically, we will have some service. It's going to be a running task scheduled. So we have our ETL process or something like this that's going to be running on this storage in order to calculate chosen top case on chosen time frames. So for 1 hour or 30 minutes, we will be calculating this like with very good precision, or if you change it to messaging queue, with the best possible precision. All right, now let's discuss further. All right, now let's discuss situation where we want the most precise data possible. So for this, as discussed, we're going to be using our events. We're going to be collecting raw events and putting them into our storage. After this, we have 2 MapReduce jobs. One is going to be counting, and second one is going to be calculating top K, and then storing them to our storage, NoSQL or SQL database, for example, where our merger service puts data. All right, great. Now let's talk about how we can relieve a memory on preprocessor because Hashmap is still pretty big one and we can do something with it. Because now we have this pass flow, which is going to be solving precision problems and problems of arbitrary time intervals. We can focus on saving memory in this process. And of course, we'll get a less precise result, but it might be okay. And in our case, we say that it is because we have this flow and because we sufficiently to show top 10 posts. And if calculations are not exactly precise and we say show 11th post instead of 10th, so because we didn't calculate correctly, it's okay for us. All right, let's discuss this preprocessor part with Hashmap. Now that we have discussed precise way of calculating top k for any chosen time interval, we can try to optimize our preprocessor a little bit more. So our Hashmap has a problem in the sense that it grows with the number of posts growing. How about we try to change it to replace it with another data structure? So let's take a look at count min sketch. What this data structure do basically is we have an event of like to some post with ID1. We calculate three hash functions. 3 is an arbitrary number, we can choose any. And upon calculating it, we get ourselves results in the span of from 1 to m. M is also chosen. All right, now that we have calculated, let's take a look what we do next. We see that hash function 1 get result of 1. So we increment this cell on 1. Hash function 2 gave ourselves a result of 3. So we increment this cell on 1. And same goes for hash function 3. All right, great. Now we have 3 cells corresponding to count of 81. How about we take another event of 81? We will just increment same cells. Now that we get ourselves event for another ID, let's say ID2, it's going okay for hash function 1 because we have another value. We increment cell 2 and it's hash function 2, we increment cell 1. But for hash function 3, we have ourselves a collision with ID1. So we increment this value and get ourselves 2, but now we have like a wrong number here because it calculates different IDs, but they were put in the same cell. Count min sketch solves this problem by having several hash functions. And now when we want to show top k, we will be taking minimum out of all cells for specific ID. So for ID1, we're going to be looking at this cell, and this cell, and taking the minimum. That will give us a 1. For ID2, we're going to be looking at this cell, and this cell, which will give us a minimum of 1. All right, great. You can choose, as discussed, arbitrary number of hash functions, and m can be any, respectively large as you want. Of course, as you grow m or number of hash functions, also grows probability of not having collisions. So collisions go lower and lower, number of possible collisions. Of course, it will also grow size of your table, so it's always a trade-off between accuracy and number and memory used. All right. Of course, by introducing this count min sketch, we introduced some probability of error in our tables because Hashmap was counting every ID and storing them all. And now we have these collisions which may produce errors. So basically we have sacrificed some precision in order to save ourselves space. But of course, because we have this path, we can do such a thing and it seems reasonable. All right, now let's move on to next section. Our requirements. So functional 1, returning top k list for specified time period. We covered it in 2 ways. First one will calculate not the most precise result, but very fast and will be available to us in manner of close to real time. And another one will calculate the most precise and also allows for calculation of any time period. For covering of non-functional requirements, scalability, we have load balancers, distributed messaging queues, our service has replicas, and so on. For performance, our flow when we using count min sketch is good, shows good performance, of course. And we can always add more processors and replicate mergers and so on. For availability, yet again, our flow of calculating will be available close to real time. Thank you for bearing with me. Click like and subscribe. Thank you.